Hey guys, welcome back to Biostat. We're going to switch gears just a little bit. We're going to put on our quantitative hats because we're going to get into probability. So far, we've stayed pretty conceptual. Probability is starting to combine the conceptual understanding with a little bit more mathematical reasoning. And so here is the layout for the probability unit. We're going to talk about what is a probability. That's a key concept. I also have a theory I want to share with you that is important about why we start to learn about probabilities from things like dice cards, various toys. We're going to talk about a number of different definitions: sample space, probability of event, complements, different probability rules. And this last bit I want to cover with things like dice, toys, cards, and also using a realistic frequency table, sort of motivate the use of probabilities in public health. So without further ado, what is a probability? Probability is a long-term relative frequency. And so the key here is the long-term aspect of this definition. Probability is the long-term relative frequency. All right, for some reason not in focus until I stand here. So this is key because it reflects an expectation of the future over a large number of trials. Expectation of the future over a large number of trials. So I think what I'm trying to get at here is we all know that a coin flip of a fair coin is 50-50, but no one can tell you what the outcome of the next flip is going to be, or the next two, or the next three, or the next five. But what we can start to say is, if I flip that coin 1,000,000 times, then half of those times are going to be heads, and half of those times are going to be tails. So before I answer this sort of fundamental question, let me define some more things. So the probability of an event, the notation that we're going to use, the general notation, is something like this. A is a generic event or outcome. Sample space. Sample space is a list of all possible outcomes of a given experiment. And what I'm going to do is put experiment in quotations, because this definitely applies to observational studies. This applies to experiment or trial or investigation. It doesn't have to be a true experiment for the sample space to work, right? It's a list of all possible outcomes of a given experiment or trial. The notation is just the capital omega. It's the Greek letter omega. And so combining our notations for these two things, we can say that the probability of the sample space is equal to 1. Probability of the sample space is equal to 1. The more you think about it, the more confused you're going to be. The probability of any of the things that are possible occurring is 1. It's basically saying that we have listed all possible possibilities of our experiment, trial, or investigation. We have contained all of it. Probabilities, of course, have to be between 0 and 1. If you ever are obtaining a negative probability or a probability that is greater than 1, you know there's something that went wrong. So now we're going to apply a bit of logic. Probability of any event is this. Probability of the entire sample space is this. We can now introduce something called a complement. Complement. So we're going to think not A, right? A is just any event. For the complement, we're going to think not A. The notation is A with a little c for complement. And just sort of using logic, the probability of the complement of A is 1 minus the probability of A. So this rule for complements is just combining everything I have on the board thus far. If the probability of falling into the sample space, which is again just a list of all possible outcomes, is 1, and we're interested in everything that is not A, then we just take this probability of not A, as 1 minus the probability of A. So together, we have covered sample space, probability of event, and a complement, but this fundamental idea about why we start to learn probabilities using things like dice and cards and toys, that's what I'm leading towards with some examples. So let's do some examples of these relatively simple concepts. And the first one that I want to do is the roll of 2 dice. Not 1, that's too simple. You guys are too smart. Let's do the roll of 2 dice. All right. The roll of 2, we can say 2 fair dice. The roll of 2 fair dice. So as soon as I say, think of 2 fair dice, because of us being on this planet for as many years as we have, we know a lot about dice. We know what to expect from dice. So we need no data to obtain probabilities. This is the key. Because we know how dice work, at least 6-sided dice, I keep changing the problem, 2 fair, 6-sided dice. We know what a 6-sided die looks like. We have, almost all of us have rolled a 6-sided dice. We know what to expect from a 6-sided dice. That means that I don't need to collect data from a 6-sided die to obtain my probabilities of interest. All right, sample space. Well, because we know that it's a fair 6-sided die and I have 2 of them, my sample space omega looks like this. I'm not going to write all of it out, but you guys are going to pick up a pattern, right? 2 1s. All right, so here are my 2 die. And right now I'm just changing the first one, and then things happen here. And towards the bottom here, I have All right, just got to get my pips right, right? These are these little dots are called pips on a die, by the way. And finally, 6 pips up on each die. By the way, these curly brackets right here indicate that it's a set, that mathematical set. Remember that our sample space is a set of all possible outcomes of a given experiment or investigation. The current investigation or experiment is rolling 2 fair 6-sided dice. All right, here is my first possible outcome, second possible outcome, and you would expect there are 36 possible outcomes in the sample space. If I was rolling just 1 die, of course, I would have 6 possible outcomes. And the other helpful thing about why we're teaching you probabilities using toys like dice, even though we want to apply them in public health, is for dice, every single outcome, because they are fair dice, is equally likely. All 36 are equally likely. And so we can just count, right? We can just count. If I was to write out a 6x6 array of stylized dice, we can just count how many outcomes there are out of 36 and produce a probability. Again, I need no data to find my probabilities. A preview for public health, we absolutely need data because we don't know nearly enough about any public health a question of interest compared to what we know about dice. All right, let's come up with an interesting event to compute a probability for. The interesting event is find the probability of a matching die. Right, I have 2 dice inside each outcome. I want a probability of a matching die. Well, again, because we know so much about dice, I can just say, oh, all right, well, I can just find this just like this. All right, so 2 1s definitely fits my criteria, 2 2s, 2 3s, 2 4s, 2 5s, and finally 2 6s. Forgive me, my dice became rather stylized. Right, so 2 1s is an outcome, 2 2s is an outcome, 2 6s is an outcome of my sample space. So I have 6 outcomes out of my sample space, each one equally likely. So the probability of a matching roll is 6 out of 36, 1 out of 6, approximately 0.167. Probability of a matching die. All we have to do in a simple case like this, just write out all of the outcomes that hit my criteria. Remember how many possible outcomes I have in my sample space? 6 outcomes out of 36, about 16.7%. All right. What if we practice now the complement? So this is where the complement shows its power, because now if I want to say probability of different dice, when I roll 2 fair 6-sided dice, it would take a lot longer to count all the times that the dice were different. But if I use my complement rule, I'm going to say, all right, well, different dice is just the same thing as the probability of matching dice complement. All right, probability of matching dice complement, I can apply the complement rule, which means this is 1 minus the probability of matching dice. All right, and I just computed that this was 6 out of 36. And so 1 minus 6 out of 36 is 30 out of 36. Or 5 out of 6. Or about 83%. But you can see this is the power of the complement rule. I'm now applying the complement rule. I don't have to count up 30 outcomes out of 36. And again, this only works 30 out of 36 because all of our 36 outcomes are equally likely. And again, the reason I know that is because I know a lot about two fair six-sided dice. Let's make it a little bit more interesting. As I drive home this point. What if we had a little bit less standard tool for asking questions? What if we had a different kind of question about the surface of the Earth? What if we had a question about find the probability that a random location on Earth is water, is in water? How about? Well, and suppose that we can't just use Google to look it up. What I have is a highly stylized model of the Earth. I can perform an experiment. I can perform an experiment by flipping my globe and recording what my finger touches. In this case, I am actually just off the coast of Africa there. So for example, my first flip, here, now I'm starting to take data. First flip is water. Land. Water. Let's do one more. Let's do one more. Water. All right, so this means my sample size is 4. Now, sample size, sample space. Don't get the two confused. My sample size is 4. My sample space, I'm using notation. Omega is my sample space. It's the list of all possible outcomes of my experiment. The list of possible outcomes of my experiment are water and land, each not equally likely. How do I know each one is not equally likely? Because I know a little bit about this planet. We all know a little bit about this planet. We know this planet is covered mostly with water. We know, in fact, that 71%, you can look it up on Google now, 71% of the planet is covered with water. High-tech satellite imagery of our Earth has shown us that 71% of the planet was covered with water. This is not a high-tech satellite imagery anything. This is a highly deformed blow-up globe from Walmart. Yet, I'm still able to perform an experiment with this to collect data. And with my sample size of 4, probability of water was 3 out of 4.75. Boy, that's close, isn't it? Let's put this thing full circle. Probability of water complement is the same thing as the probability of land, which is 1 minus 0.75, which is 0.25. Okay. So I'm going to drive this home. So please pay attention right now. With dice and with questions about the planet, we know a lot about the data generating process. We know a lot about the data generating process. With the dice, we know each roll occurs 1 out of 6 times. With the Earth, we know that 71% of the planet is covered with water. So when we obtain data, it is not a hard sell to say that if I continue to roll my die 1 trillion times, then 1/6 of my trillion rolls will be 1s, 1/6 will be 2s, 1/6 will be 3s, so on and so forth. It is also not a hard sell, even with something as deformed as this, where I definitely get measurement error because I'm lazy about, maybe covering, oh, there, I got land. Even with a tool as rough as this, I can still measure data about the Earth. And I can provide evidence in favor of this, remember, population quantity. So we start to teach you probabilities because these things are known, and we can use data to build arguments about what happens as the number of trials gets close to infinity. In public health, you're looking at it the opposite way. You don't know this number. You don't know this number. All you have is noisy data. All you have is noisy data. And you're trying to infer the population quantity that produced this data. So the way that real research works is backwards than the way we roll dice and we think about Earth's surface. So how do I summarize that? In research, we work backwards relative to dice, cards, coins. We take samples and obtain noisy data. Why do I say noisy data? Well, because we just finished learning about all the possible biases that can affect your experiment. Why do I say noisy data? Well, my tool could be rough and I could have measurement error because of my measurement protocol. And then we try to use this noisy data. When I say noisy, I don't mean sound noise, I mean statistical noise. We try to use this noisy data to infer the true data generating process. I can be flipping this globe 1,000,000 times to try and infer what proportion of the Earth's surface is covered with water. I can be rolling a die 1,000,000 times to try and infer whether it's fair. But when we are using toys, we know the true data generating process. And this helps us understand this randomness of the next flip, the randomness of the next die roll. In real research, we only see the data and we try to infer the true data generating process, the true proportion with which a water will occur. So this lesson will be 2 videos. So I'm going to end this video here, and I'm going to pick this up with probabilities in a frequency table. Thank you, guys.